Okay, so here we're going to talk about estimating the relationship between two or more variables. And so using the value of one variable to predict the value of the other variable. Sometimes we use values of multiple variables to predict the value of another variable. Whatever we want to estimate or predict, we call that a dependent variable. Dependent variable. So this will be the y variable. Y variable is a dependent variable. And then the variable that we are using to predict the dependent variable, we call these independent variables or predictor variables. This is from your textbook. What is this example? This is a fictional company, a Butler trucking. This is like the trucks that make deliveries to different places. So think about those Amazon trucks or UPS trucks that come and deliver the packages that you ordered. There's different trucking companies. Some trucking companies do deliveries for more like the companies from like the warehouse to the retail stores. But they like to do a better job of giving driving assignments to their drivers. So they want to be able to estimate how long it will take to go for the driving assignment to finish the entire route of the deliveries. So they collected some data. So they figured that the travel time should be related to the number of miles traveled. Okay, so for example, here's a small set of data they came up with. So let's say they look at the last 10 driving assignments, and they found this kind of data. So the first one, took 9.3 hours for the driver to finish the entire trip, and it involved driving for 100 miles. So drove for 100 miles. And it took 9.3 hours. And so while they're driving, they're dropping off. They're stopping at places and dropping off the shipments or packages. Okay. And then number two, it took only 4.8 hours, and the miles traveled was 50 miles. Okay. So here's the x variable, and here's the y variable. That means you're trying to use the mile travel to estimate the travel time. Well, we might say, well, we already have the travel time here, so what do you mean by estimating? Well, you want to estimate this time for future driving routes, for the unknowns, the driving routes that have not been completed, so that they could maybe estimate how long it would take, so that they could tell the driver, here's how long we expect your trip would take, so they could plan accordingly. We are already given we're given the data set. Now we are going to build a model based on this, and then we're going to use that model to make prediction for future driving assignments. So what is the appropriate kind of chart for this kind of thing? When you're trying to find the relation between two quantitative variables? Scatter chart. So it's a scatter chart. So where scatter chart means that you have x values in horizontal axis and y values on the vertical axis. So we're going to make a picture of this. So I'm going to take these and then insert a scatter chart over here. Okay, so here is our scatter chart. Okay, so remember that the first column is going to end up on the horizontal axis, which is what we want. We want x to be on the horizontal axis here. Now, of course, so we should always label the axis. Right? So chart design, add chart element, axis titles, more axis title options, and this part is already selected. Miles traveled, okay, which is x. And then here I'm going to say time, that's going to be hours, that's a y, so maybe okay, so we got this, and now remember, if you want to, sometimes you might want to kind of just make it clean, so get rid of the grid lines, yeah?
What's the shortcut where you can click the label? Do you press equal and then you can select the
cell? Oh yeah, right. So here you could say, you could kind of select the thing and then you start typing and you say equal, type equal, and then click.
Oh, okay.
Yeah, and then do this. Yeah. And here we want to give it a proper chart title, so we're doing miles versus time. Miles versus time. I think that's enough information. Okay, so we could insert trend lines. Remember how we do that? Click on one of the dots, right click, and add trend line. And now we're talking about regression. So we want to ask for the equation. We want to export the equation. This is your regression equation. That's your model. And the y and r squared, what is this? Oh, we're going to talk about this as well. So let's ask for it to our display r squared. Okay, so we're done with this. So let's get out of there. Okay, so I could see this better. Okay, so we have basically built a regression model. Okay, so y is equal to 0.678 times x plus 1.2739. So that's a regression model. So you have here there's the slope and there's the intercept, right? Slope is the 0.0678 and the intercept, or we call it y-intercept. Y-intercept is 1.2739. Okay. In regression, it's customary to put the constant first. So this one first. So we might write it this way. Y is equal to 1.229 plus 0.0678 times x. It would be better if you, instead of using x and y, to use the names of these variables. Time, this is in hours, so it's useful to also indicate what units it is. Time in hours is equal to 1.2739 plus 0.06678 times A times miles. So, but now this is easier to understand. Now, is this a real time? This is really like estimated time. And this one is 109.3. So that one is your first data point. 9.3. So that's this one. Now, if I plug in 100, what do I get? Here, that's your y hat. The estimated value. Here, estimated or predicted. Estimated time, or we call it y hat. To get this value, I would plug in 100, where miles equal to 100. The estimated time is, and then you just plug in the 100 plus 0.0678 times 100. This is going to be 6.78, so it's 1.29 plus 6.78. Come on, 6.78, so you get 8.05. So this is your estimated time when miles is equal to 100. Okay, so this way we could make predictions. Now, suppose you have driving assignment with, let's say, 60 miles. So now we could estimate the time. Estimated time is, let me say, now if you look over here, now I don't see 60, but because I have this line, I could make the prediction. This is over here, when x is equal to 60. And what I'm trying to do is, I'm trying to find the corresponding y value on this line. If I go like this, what is the, what y value does it hit over here? Okay, so we could get that value over here by using this equation. So I could say, it's 1.2739 plus 0.0678 times 60. That gives us 5.34 hours. Here, okay, so this is, after typing this, I got this value. So if you have a new driving assignment that's involved like driving for 60 miles, then we could say we expect it to take about 5.3 hours, a little bit over 5 hours. So for any value, any number of miles along here, I could make predictions by using this line, because I have the equation that corresponds to this line. So from looking at this, you could see that there's a positive relationship in that when the number of miles is increased, that is, as you go this way, the time tends to increase. When x goes up, then y is going to go up, and then when x goes down, so if I go from here to here, if I decrease the x, go this way, and then y value will fall down. So y value will also decrease. In general, that's the pattern. So this is a positive relationship. What kind of relationship? So that was a positive relationship. Positive relationship. Okay. Slope is positive. So the slope kind of depends on the kind of variables that are being used. So slope could be like 100 or 10 or 1, depending on what units you're using. So if you're using like minutes instead of hours, then the slope is going to be different. So we want something that's kind of standardized. So it's kind of like standardized number is a z-score when you're trying to see how far a value is from the mean. And so here we want to see like how strong is the relationship. So the standardized value for it is a correlation coefficient. So what does correlation coefficient do? It gives you two things. It gives you the strength of the relationship and the direction of the relationship. Direction means positive or negative. So it has the same sign as a slope. So if the slope is positive, correlation is positive. Slope is negative, correlation is negative. And also gives you strength that's not affected by the units of the variables. So it's between -1 and 1, and we could interpret it as if it's close to 1 or -1, that means it's very, very strong. If it's close to 0, that means it's a very weak relationship. Okay, so let's take a look at some pictures here. Okay, so take a look at this one. The correlation coefficient is equal to 1. So it's like exact, so this is the highest you could have. Like this is the strongest possible, right? So that means relationship is so strong that if you know the value of x, you will get you are able to predict the value of y exactly, because it's all in a straight line. So if you know the value of x, then you could predict the value of y with perfect accuracy. Now here is another strong relationship, but the direction is opposite. If you're here, now if you increase the x, what happens to y? Right, like that? Right, it goes down. So it goes down. So y decreases. So it's the opposite relationship. So if you increase x, then the y is going to decrease. Okay, so you have negative relationship, but this is still a strong relationship because the strength doesn't say anything about the direction. Strength has nothing to do with the direction. Strength means, is it close to that line? No, is it really close to that line? Does it fall on the line? So here, if all the points fall on a straight line, then you have the strongest possible relationship. It's just in this case, you have a negative relationship. Now, this is like an opposite case. R is equal to 0. So there is no relationship. And how do we know there is no relationship? From this picture, you could see that the line here is horizontal. The line is horizontal. So that means when I increase x, what happens to y? So if I go to the right, what happens to y? Nothing. So because y stays at the same level. Here, as you go from left to the right, this line is flat. It's horizontal. There is no slope. So there's no increase or decrease in the y value. Y value is the same. So here, the values of x are not related to the values of y because changing x doesn't have any effect on the value of y. So here you have no relationship. So 0 means no relationship. Let's look at this one. And so this one has some relationship. So you could see that there is a positive slope here. It's going up. But it's not it's not very clean and neat. It's just kind of clouds of points. So you could see there's some pattern like this straight line, but the points are just scattered around the line. They're not very close to the line. So here you don't have a perfectly strong relationship. So here we might say you have a somewhere in the middle, like a moderate, or say moderate relationship. So that's when you have a correlation like around 0.6, 0.5, like that. And on this one, it's the same thing except the direction is reversed. Here you have negative kind of slopes. You also have negative correlation. So here's a summary of what we just said. Close to -1 or more, strong. Close to 0, that's a weak relationship. If it's very close to 0, we would say there is no relationship. Positive means positive kind of this way. It's kind of tilted upwards like this. Negative means it's tilted downward like this. How do you describe the strength of the relationship? We could say weak relationship, moderate relationship, and or strong relationship. This is the number line. So you have number line here, you have -1 here, and +1 here, and then here is a 0, and here is a 0.3, and 0.7, and then to the left is -0.3, and -0.7. Okay, so if you're close to 0, so that's what this means. The absolute value is between 0 and 0.3, and so that means R is between -0.3 and +0.3. Okay, so that's over here. So we say there is a weak correlation. Or we say weak relationship, either way. Okay, if it's right at 0, that means no relationship. No relationship. Okay, now if you are somewhere kind of here or here, between 0.3 and 0.7, or between -0.3 and -0.7, that's what this means. And so that's what this means. After values between 0.3 and 0.7, then we say there's a moderate correlation. So here we would say moderate relationship, and there's moderate relationship. So now here, if you're close to -1 or close to +1, then we say there is a strong relationship. And of course, we would say, if you're here, then you have positive relationship, and if you are here, then there's a negative relationship. Negative, and there's a positive. So how do we get the correlation? So correlation is this function correl, okay, and then parentheses, and you specify those two columns of values, miles and time. So correl, and then this one, B2 through B11, comma, and then C2 through C11. And so using this, we got this 0.815. So 0.815. 0.815 is the correlation. Okay, so that is, we use a letter R for correlation. Now, there's also this thing called R squared that's shown here. So that seems like if I square this, probably I get this value. And so let's try that. So if I go this number, and then the caret 2, that should give me the square. So at 0.815 squared, that gives me, okay, so that gives me 0.6641. So again, I took this value and squared it. So that gives me 0.6641. So you know the R squared here is just a correlation squared. This is R squared, which is also a very important measure that we'll discuss a little bit later. So it's a little bit of theory here that the regression model is based on. Let's see, our ultimate goal is to build a regression model that describes how the numbers interact within the entire population. So this might be all the possible driving assignments ever. All the possible trips. Trips. All the possible driving trips, past, present, and future. And so we want to build a model that describes the relationship between miles versus time. We want this relationship for all the possible driving trips. And we were able to get that relationship in this kind of format. So this will be like some constant value, some kind of slope here, times the x. So where x is the miles, and the y is the time, and plus some little factor here. Okay. And what's this little factor here? It accounts for the variability in the time that cannot be accounted for by the miles. And so it kind of describes the fact that if we have, okay, so this is not a perfect model because there's always some variation. There's always variation. For instance, like if you have 100, if x is equal to 100, okay, your prediction is here, but the actual values are different. Actual values, some are over here, some are down here. So there's variability. There's a variability. So if you drive 100 miles, can you say how long it'll take exactly? No, it's going to be different, depending on what? Depending on other things. Depending on the weather, depending on the traffic, depending on the driver. So depending on many different factors, it's going to vary. So the number of miles doesn't completely determine the time that it'll take. Okay, so there's a lot of other factors that we're not including when we just use the miles. So it points to the fact that here there's some variability. So this is kind of like we call it error factor, error term. So this just says that this part is not enough. Number of miles is not enough to perfectly predict the time. There's this other factors, and or whatever other factors are, we just put it in here. So this is like this kind of a catch-all term that describes the variability based on some other factors we didn't account for over here. Okay, this is a model. This is a model, kind of ideal model, but we're never able to get these numbers because we don't have all the possible driving trips. We don't have the entire data set. So what we do is we just take what we know. So we just have this 10 driving trips. So based on 10 driving trips, we are building this model. So the model that we built from the sample of the 10 driving trips is over here. This one. This is what I'm talking about here. So y hat, that's this one. That's this one. V0 is 1.2739, and V1 is 0.0678. X is the mile. So when we use this equation, we gotta keep in mind. This is just a substitute. This is a substitute we are using because we don't have all the possible trips. This is only based on the sample data we have. So we call this an expected value. Expected value of y. Not the perfectly accurate value of y, but it's expected value of y. So for example, suppose, let's say x is equal to 60. Let's say y hat, we get 1.2739 plus 0.0678 times 60, and that gave us 5.3. So this is the expected time if you are driving 60 miles. And the idea is actually it's the mean, it's the average value. You drive 60 miles. And so in reality, when you drive 60 miles, sometimes it'll take 5 hours, and some other times it might take 6 hours, and sometimes it might take 7 hours, sometimes it might take 5.2 hours. So there's a bunch of numbers that you could have when you drive 60 miles, depending on which driving trip. But if you were to average all the driving trips that have 60 miles, we would expect it'll be about 5.3. So now let's talk about estimating the error term. So we talk about the residual. Residual is the actual value minus the estimated value. For example, so let's say x is equal to 100. Y hat would be 1.2739 plus 0.0678 times 100. Okay, actually, let's put x here, and let's put here 100. So here, what I do is I just point to this. Okay. So we could estimate the y value this way. Now, what is the actual y? Let's look at the actual y. Actual value was 9.3 from here. Okay, 100, x was 100. Here, actual value is 9.3. What if it's, let's say, 50, like over here? Here, I'm going to copy this down. Okay, and the actual value was 4.8. Okay, so here I'm just looking at the first two assignments right here. I'm looking at this part. Let's talk about the residual and move this a little over. So here is actual minus y hat, minus y hat. So here I'll be going, okay, well 9.3 minus 8.0539. Okay, and then here I'll be going 4.8 minus 4.6639. So that's that minus that. Okay, so that is a 1.25. All right, 1.25, and here's the 4.8 minus 4.67 or 66, and that gives us a 0.13. So again, let me make this a little bit, so too many digits. Okay, so we get something like this. So this is the residual. This is the residual. So actual value minus the predicted value, that is a residual. And why do we even worry about this? Because these are the numbers that are important to later verify that the model is appropriate. So we do a lot of analysis with the residuals to make sure the regression model is correct. Later when we verify that it's a good model. We could do this for all these values, any driving assignment. Okay, so for example, suppose let's say you have a trip with, let's say, 70 miles. 70 miles, okay, and the actual time was 6 hours. Then what is the y hat, estimated or predicted time, and what is the residual? Okay, so let's do this together. What is the estimated time? Okay, so I have to go y is equal to 1.2739 plus 0.0678 times what? Times 70? Okay, so times 70. Right, so I have to do that. Okay, so let's see. So I have to go 1.9 plus 0.0678 times 70. So that's my answer. About 6.0. So now the residual would be actual value minus the y hat, so it would be 6 minus the estimated value. So it will be like a negative 0.0199, so you have a negative residual in this case. Okay, so what is meant by the numbers in the regression? Let's make sure we know what those numbers mean, like the slope and the intercept. So that was the equation. So that's your b sub 0, and here is your b sub 1. Okay, so this is 0.0678. So this is the estimated change in the mean of the dependent variable y that is associated with 1 unit increase in the independent variable x. So basically it's a slope. So remember the slope is so rise over run. So change in y divided by change in x. So it's a rate of change in y. So if you increase x by 1 unit, what will happen to y? So it is increase in y, or we'll just say change in y per 1 unit increase in x. Okay, so that means, for instance, if x goes from 60 to 61, okay, then y will increase by 0.0678. And then here, what does this mean, 0.0678? So now, if you actually have to make sense out of this, you got to think a little bit. Y, remember, was the time. So this was the hours. How long did it take? How many hours, right? So the time will increase by 0.0678 hours. That sounds kind of awkward. Maybe, how about convert to minutes? Let's convert to minutes. Now, how do you convert this to minutes? Just multiply, right? Multiply 60. 0.0678. 0.067 is the increase in y per unit increase in x. Okay, and that's 0.0678 hours. So in minutes, it is 0.0678 times 60. So that's 0.0678 times 60 is 4.068. Let's just say 4 minutes, roughly 4 minutes. So this implies that if need to drive 1 more mile, the trip will take, on average, first, it's all on average, 4 more minutes. Now, if you drive, what if you drive 1 fewer mile? Then the trip will take what? On average, and what would you say? 4 less minutes, 4 fewer? Yeah, 4 fewer. 4 fewer minutes. So we know what this means, 0.0678. So it's an increase in y per 1 unit increase in x. Or you could say decrease in y per 1 unit decrease in x. Okay, so like this. Now, what about this number, 1.2739? So that is the number over here. So if I were to extend this thing, right over here, okay. So over here, that's the y-intercept, and that should be about 1.27. So that should be your v sub 0, or the y-intercept, 1.27. So that says that when miles is equal to 0, we expect y value to be about 1.27. But that's probably not a good interpretation, because if miles is equal to 0, what does it mean? Can you have a trip that has 0 miles? I don't think so. If you are not moving, then you're not delivering anything. So that has no trip, no driving trip. So it doesn't make sense to say, well, if you have 0 miles, okay, but then we expect it to take 1.27 hours. So that makes no sense. So you have to be careful, when you interpret this. And so what we could say is, maybe you could think of it as a kind of like a fixed cost. In accounting, you have the fixed cost and variable cost. And so like in simple terms, you could say, okay, what's the total cost? Is the fixed cost plus a variable cost, and variable cost depends on whatever number of units you're making. So here you could think of it that way. So you could say, well, let's see. This part, 0.0678x, okay, so this part depends on x. So this part depends on the number of miles. So that's kind of like a variable cost. And then this part doesn't. This part just sitting there is 1.27. So you could think of like a fixed cost overhead, kind of thing. So you could say, well, maybe this is a time that you don't spend driving, like during the trip. Because like you're driving, and then sometimes you gotta stop and then make the delivery and then get back in. Sometimes you have to stop and take a break. So there's like a lot of times that you're not driving. Thinking about time that you're not driving if you're the driver, right? So maybe this is a driving time, and then maybe that part is the part that's where you're not driving. And so you could think of it as this is a non-driving time. I mean, I'm not saying that's perfectly accurate, but there would be kind of reasonable, interpretation when you look at this equation. Okay. So, but if you are when you're making predictions, you don't want to go like too far this way or too far that way. So you want to make predictions like around here, or maybe a little bit to the right, a little bit to the left, but you don't want to make predictions like way over here. In this range, then it's about pattern looks like about a straight line, but beyond that we don't know what's going to happen. Beyond that, maybe it might kind of bend down like this. Like who knows? And so don't go too far when you're making predictions. So what I mean by that is, so here are the x values. Smallest value is 50, right? So this is between 50 and 100. X values are between 50 and 100, in your data. So between here. Okay, so you might make predictions for x equal to 60, 70, 51, 52, maybe 110, or maybe 40, but don't go too far, from the range of your data. Okay, so that is something to keep in mind. So extrapolation, don't extrapolate too much. Don't go too much outside your data region.